Hey guys, welcome back to the channel. Welcome to a new type of video where I start to react to different research things, and I thought, why not react or go through my own PhD thesis? So you can see on the title, I'll be now going through my PhD thesis. I have not read it for a while, not gone through even for ideas or inspiration. So I thought that'd be a good video just to share and walk you through my thesis and share some stories about how I did this, or some funny stories about that, or some informative tips that I may have realized whilst I go through my thesis. So it's gonna be maybe quite a bit of a long video. I'll try timestamp it where I can. If you're new to the channel, my name is Amir Hussein. I love to talk about research, so much so I decided to make YouTube videos and Instagram posts, as you can see over here, to help researchers with tips and advice for the research life. So if you are interested, do consider subscribing, click the post notification bell so you don't miss out on when I upload, because I'm now trying to upload 2 videos a week for you guys. So if you can, do subscribe, and you'll hopefully have more videos like this as well, not just kind of me talking about tips and advice, but something interesting and maybe humorous for you to enjoy. So without further ado, let's head over to my thesis. So you see on screen is actually my thesis. You can actually find this online. I'll put the link to this in the video description if you wanted to have a proper read. It's published online through my old university's repository, so if you do want to check it out, feel free. But right off the bat, a fun fact, and this is also useful for those who are doing research or doing PhD. For motivation, I actually made this cover page way before I actually started writing. I actually made this maybe 3 or 4 months before I was even close to finishing any research. So that's actually advice for you guys. If you are interested, get it set up. It'll be motivating for you to start writing, because many of us actually, unfortunately, suffer from kind of anxiety or procrastination in terms of research writing. So yeah, that's actually something I started off with way before I did my writing. So going back down, as you can see, I actually finished it in 2018. Then I graduated the next year, middle of 2019. And then looking at the abstract, mine was, as you can see here, like kind of intros, methods, and then main findings, and then discussion. But fun fact, I wrote this at the end of my actual thesis. So for those who are thinking, oh, how do you write abstract? Don't write it yet. You write it right at the end. They say that, and I think I did it as well, that you write the introduction last. Then once you've done that, then you actually come in and write your abstract, because you'll then know where you actually need to go in terms of the conclusion and the discussion of your thesis. From memory, if I can remember, and I'll put it down here on the screen, you talk about your results first whenever you've got it, put that into your thesis, describe it, then look at kind of the conclusions about key elements you're learning it from in terms of your further work, the combination of your findings. Then you set the scene with introduction, and you slot in key questions about why is this important, why is that important, and then when examiners are reading that, that actually leads them on to how you've answered it using your actual PhD and your thesis. I'll link down a Instagram post I actually did about this down below. I'll put it over here as well so you recognize the thumbnail. That's very important in terms of structuring your thesis. But as you can see here, I've not even mentioned what my PhD was about. You can see over here, the combination of my research in my PhD was about the notion of anti-angiogenic therapy. So not to make sure this is a lecture, in simple terms, tumors need blood vessels to grow. They need a blood supply for oxygen and nutrients. And there's a process by which tumors grab that blood supply, and it's known as angiogenesis. It's usually when you get cut and stuff like that, but cancers use it pathologically. But there's a notion of anti-angiogenic therapy, which is trying to regress or block that blood vessel formation from occurring, so tumors never establish a blood supply and can never kind of start to metastasize. Because that's the key hallmark of them becoming a dangerous thing in the body, is when they establish a blood supply. So my thesis was looking at some naturally derived compounds in the lab that may show some promising anti-angiogenic activity, and did some kind of simple testing to see which one could be processed further as a preclinical candidate for drug discovery. So that was the combination of my research. So you can see over here we've got these were the compounds, by the way. They're called Chalcones, or 1,3-diphenylpropanones. This is crazy to look back at my actual thesis. And then you got, this was actually the main compound. Nothing's patented, nothing's going to be published anyway, so I'm not too concerned about, showing. It's already in the public domain, so I'm not worried about people reading it because anybody can. So don't worry, don't feel alarmed that, oh, you're showing your research. This research is kind of old, but there's some lessons to learn that hopefully you guys will learn anyway. If you're interested, this is the mechanism by which I made these compounds. The cell line that I used was Huvex as a angiogenesis model, so human umbilical venous endothelial cells, if I remember. And then I use a colorimetric assay to assess which compound was interesting. Then I did a model or a function assay known as a Runhe scratch assay. And then I did some mechanistic work to try and figure out what is actually happening for the interesting compound. And then you can read this if you want to in terms of main findings. But that's actually how I set up my thesis in terms of abstract. Then communications. So as many of you know, if you haven't watched this video, well, the link up here is the story of my PhD, how I suffered a lot from many different things, and I didn't get a chance to actually go to an international conference and didn't get a chance to publish my research. I'm actually trying to finish a paper from this PhD actually, and to try and get out something as a first author from this. But I was able to, get some abstracts in. So I've got one in cardiovascular research, which I think my colleague, my first supervisor, was actually able to go to Vienna to present for me because I didn't have the funding to go to, which was annoying. And then another one which, again, colleagues were presenting for me because they got funding to go. These were my supervisors, they got funding to go, and I didn't. And now looking back, I realized that that's really frustrating that I didn't get funding, and I still haven't been to an international conference yet. So anybody who's watching who has sponsorships and wants to, help me out, feel free. But I know that's a long shot. But those are some kind of conference proceedings that I do have the ISBN number, so I can talk about them. And thankfully, these were what I've been talking about a lot in terms of awards that I won. So this was me winning first prize in my university-wide poster competition. Then I think 2 years before that, I won the oral presentation for my research. And then I think I became runner-up. Funny enough, I came runner-up, but I had the same poster that won me this. But obviously I just changed the terminology. So I was wondering, did they just didn't want me to win both, maybe? And I felt sorry for everybody else. Who knows? But very grateful to win these, and because they've been really good lessons to learn in terms of sharing how I presented, how I made my poster to help you guys, so you guys can have better posters and better oral presentations. And then I believe was cytobiology. Yes, I believe I'm trying to remember when I did this. This was with a very, very close friend of mine and his supervisor at the time. He's got his PhD now. It was on, yes, looking at a sub-part of my PhD, and we published some of the findings in a poster that was done at the conference. So that was that there. And then acknowledgements. I think with this, I'll let you read yourself because I don't want to overrun it. But some bits I do want to talk about that I think are important. And start off with one is Dr. Ruparelli, who was my second supervisor, who's been a great friend of mine, who's somebody I admire, I respect a lot. We had our differences, I'll be honest, and I think he knows, where I felt he wasn't there much when he should have been and stuff like that. But he's such a great person and such an honest researcher that before I even met him, I remember I knocked on the NMR door, so the door that has the NMR machine, nuclear magnetic resonance. It's a analytical chemistry technique for those who may not be aware. And I remember I knocked on the door and I just pitched an idea to him about cancer and diabetes. And then long behold, a year later, he became my supervisor, and then 4 years later, he has a student who got a doctorate. But there's many people to say thank you for, my main supervisor at the time, Dr. Fretwell, and then Harpreet Singh, who came on board at the end, was really, really integral, who I class as my first supervisor towards the end, because he was really, really, really integral in me getting on his board. Dr. Ken Beresford was a genius, you know, who knew so much but was never really kind of utilized as much, and I felt bad for him because there's so much more that people could have utilized him for, but politics and stuff like that, you know, annoying. And then many of my friends at the time who were integral, Jay, who just finished his PhD actually, showed me a lot about the Western Blot stuff. And then two of my kind of heroes, I would say, my kind of brothers, elder brothers, I would say, and Ibrahim and Abid, Abid. I don't know why I pronounced his name wrong. He's gonna kill me if he finds out I pronounced his name wrong. But yeah, these are just some kind of tips in terms of acknowledgements for you guys. But I think it's this that I want you to read yourself. I don't want to do injustice by trying to emphasize it. It's page number 6 of my thesis. Read it yourself. Page number 6 and page number 7. I don't want to, you know, spoil it for you. This is very personal in my thesis, but the reason why I felt sort of comfortable enough to share is I know many other people are going through something like this, and it was a testament to say that, look, if you're close to your family, your spouse perhaps, your brother, your sister, whoever, your friend maybe, that is a bond that's also worth noting as integral part of your success. And my mother has been a huge part of my success, and wherever you are, whoever you are, look after your parents. Believe me. Nobody's going to live forever, so keep in mind, look after your parents. But anyway, as I mentioned before I double on, read this on your own time, and let me know what you're thinking down in the comment section below, because I'm interested to think about what you think of page 6 and page number 7. But you will go further. Abbreviations, don't forget them in your thesis. I had many, I don't know, can't remember half of these. But yeah, we'll skip over that if that's okay. Got this contents page. So think of your introduction as a upside down triangle. You know, you've got, I start off with cancer, and then within cancer with subset of tumor progression, and then in followed with angiogenesis. As you can see, I mentioned about angiogenesis and its, you know, key stimulators, and then I went to anti-angiogenic therapy, and then the limitations, the problems with it, because that to set the scene about what is the issue with it, and how is my PhD trying to fill or solve the problem, or trying to fill a gap. And remember, any thesis you do, it's any research you do, actually, to be fair, you're trying to either solve a problem that's out there, or you're trying to fill a need that's needed, you know, fill a void that's needed, or trying to fill something that's important. So keep that in mind when you're looking at your research, and kind of set the scene in terms of the drug discovery element, you know, because my research was on drug discovery. So remember, you got to set the scene very early on about, okay, why are you looking at these compounds, these drugs in particular? And you can see here I mentioned the importance of the preclinical drug design, about how people look at preclinical candidates. So like I said, you know, do have a read of this if you wanted to. And then I set the scene about looking at analog-based drug design, because there are computational models, there are other models, and I pose the case of why are analogs, so like derivatives of other compounds, really important. It's because of X, Y, and Z. Here are my analogs. You see, because everything's a story, everything's succinct, there isn't something that's missing. Because your thesis is essentially a story. And then we've got, you know, my aims, objectives, then how I made those compounds, which is all to do here. These are different methods of making those. I remember now, I can't believe I've made all of these. Crazy. Then I screened them. So these are remember that colorimetric assay I talked about earlier? This is what this was about. So with my thesis, I had an introduction, result, and discussion for each chapter. You know, so I had a little mini intro. Methods were all together, which is at the end. I'll mention that towards the end. But that's how I structured my thesis. So as you can see here, these are the kind of the different groups of compounds that I made actually. And then we obviously tested them to see which one was interesting. There's rationale why. Then chapter 5 was the functional kind of analysis of the parent compound, which is AH1, and the interesting compound that I found, which was AH9. And then I looked at the mechanistic activity, as I mentioned earlier. So pharmacological evaluation, I looked at these proteins in particular. And then conclusion, and then obviously experimental is here. So that was kind of the story of my PhD. Now, you're probably wondering, why is your materials and methods at the end of your thesis? So here's where it got really difficult for my PhD, and this is why I wanted to make this video, to share some nuances that may be beneficial for you. My PhD was split between medicinal chemistry and pharmacology, so there wasn't enough compounds to make it a full medicinal chemistry thesis, and there wasn't enough pharmacological testing to make it a pharmacology thesis. I was kind of in the middle. So in terms of styles of thesis, whenever you have a chemistry thesis, because there's so much analytical data and compounds, all of that is put at the end of the thesis, so it doesn't chunk up the actual story itself. Whereas pharmacology and many other theses and materials and methods are normally after the aims and objectives. So I had to wrestle with my non-chemist supervisors to understand that, look, this is how it's done. And then you can see at the end, I've got the biological procedures, the methods over here. So for those of you who have, multidisciplinary thesis or research, keep in mind which one flows better. What I was talking about is, think about what structure flows better, not just what looks better, but what is easier to read. Because something might be too chunky in the start of your thesis, which will deter examiners, which will deter readers. So you want to look at all of this is better to stick at the end, and if they want to refer to it, they can refer to it. But this is what works for me. If it works for you, great. If you have only a few methods and materials, maybe you can slot it in the middle, so it's easier to maybe to refer back to. So it's whatever works for you. This is what was working for me. Going down further, we've got the tables of figures, then we've got the tables of tables, and then we had, I think, table of something else. Yeah, tables of schemes. So these schemes are the mechanism. That's how I did the reaction, which I probably couldn't even write out now, in all honesty, because I'm not in chemistry anymore. So yeah, it was a different life back then, a different life, unfortunately. So, introduction. I have no idea how long this video is. I'm trying to look at the thing, it doesn't tell me, but we'll see. I hope you don't go away. If you want to grab coffee, pause the video now, grab some coffee, and come back. You can do. But back to the video. Introduction, obviously, as you saw earlier, upside down triangle, start off with cancer, key kind of topics around what cancer is, and then I went further down, looking at, the mortalities and issues around it. Then what I wanted to show you is something I actually drew on my iPad at the time. So my iPad's actually here, just giving me some light over here. So I actually drew this on my iPad, on Adobe Draw, I remember, and then I just added in these. So anybody who's doing anything remotely related to cancer, so if you're watching this and you do anything remotely related to cancer, this is a very, very famous paper, one of the key kind of hallmark papers. It's actually called the hallmarks of cancer, I think. So I'll be surprised if you haven't heard of this before. So that's actually quite important for those who are in cancer research. So yeah, I decided to set the scene with cancer, and then looking at this one in particular. I think you should see on the screen. That's the hallmark that I wanted to focus on. But you can see that I'm setting the scene, and then I'm going in. Talked about, some of the different parts of the hallmarks of cancer over here. Resisting cell death, apoptosis. And I had to be very key about not going into too much detail, because this is not the crux of my PhD, whereas the other one is. Going a bit further down, these are all the different hallmarks, immunoediting, and then I focus on angiogenesis. Talking about the process, so the different types, there's intersusceptive, there's splitting angiogenesis. These are the something I adapted from a paper. And you can see here, this is what tumors use. They basically, it's like a tree and a branch, something I mentioned before, where they poke out on a new branch from that tree to give itself its own blood supply. But again, feel free to read if you wanted to. Then I mentioned about the process of angiogenesis, going in step-by-step process. This is the key. It's not getting into the grits of it, the detail of it. I'm going a bit further down. And then, I don't know why this is... Look, I found an error in my thesis. Oops. I think this thing is a formatting error. It should have been obviously here. And these are the stimulators and inhibitors, and I was focusing on this in my thesis. in my PhD. And again, I drew this on my iPad, trying to show, tumor cells and blood vessels. Looking back, I probably could have done a better job, but it was enough. And I think that's what you got to look at, what's enough, and then you can add more for your papers and for other contributions. And then I looked at obviously targeting angiogenesis. Folkman was a key pioneer in angiogenesis. So within your research, you'll have those few names that are very, very prominent. So Folkman, I remember these, Ferrara, Kerbel, these were like key players in the angiogenesis research. I remember there's one statement here. Yeah, so in tumours, the balance of angiogenic stimulators and inhibitors is altered, thus the angiogenic switch is turned on. I remember this as a key, statement that showed the importance of angiogenesis. Again, this is another diagram that I drew in my thesis, showing just the stimulators and inhibitors, where more stimulators means it's turned on, more inhibitors naturally turned off. And this is something I want to bear in mind and tell you all that don't be afraid to make your own diagrams just to break up the text, because it shouldn't be too text heavy. We focus so much on the data, and rightly so, but your examiners are going to read it, so you don't want to make sure that it's too text heavy and it's bored to read. It has to be enjoyable to read, not just the writing flow, but also what they visibly see. It shouldn't be a picture story because it's a thesis, but it should also be about, right, this is actually quite interesting, there's a picture to relate to it, and it engages them to read on more and more. And this is a very famous one from Nature, which I was able to adapt, for another better phrase. And then talking about the stimulators and their receptors. VEGF is a very key part of angiogenesis, vascular endothelial growth factor. And then this is a diagram that I drew about kind of the pathway, looking at, these are some monoclonal antibody, a drug that targets key parts of the pathway. And then I actually used this to show where my compound actually started to affect from what I could see. And this is where I started to learn more about the mechanisms, transitioning from chemistry to biology. Again, so this was just on PowerPoint, I believe, but now you can use Canva and everything else. Back then I didn't know because I wasn't in the Instagram Psychom community. So if you aren't, get in. You'll see on the screen now. Follow me if you would like to, and many others that you'll find through my page. Then it gets another diagram about the receptors. And going a bit further along, this is something that I really enjoyed finding, and this was showing a summary as to when tumours grow, there are more and more players that are really important. So when you start off, VEGF is the most important, which is why we focus on VEGF to stop it at the source. But as it gets more vascularized, other players start to come in, which are really important. So then talked about that going forward, and then looking at how, normal tissue looks like this, is nice and clean, but tumor vasculature is very irregular, looks like spaghetti. And just showing that how that spaghetti kind of conformation makes it difficult for drugs to get into or drugs to get through. So like that poor drug delivery is a key part, but also how some anti-angiogenic drugs help to normalize from this spaghetti structure to this straight road structure. So what we call vascular normalization, and that was helping the chemotherapeutic drugs to get in. So that's what I was talking about here. So I still remember some of my thesis, still remember some of it. And then looking at, some non-VEGF triggers of angiogenesis. Even though angiogenesis is very important, VEGF is very important, there are some ways that you can turn on angiogenesis without using VEGF. So I remember I had to mention about this in particular. And then going down further, talk about angiogenic therapy, even though I can't even pronounce it still properly. So you've got the three players, some that antibodies that neutralize VEGF, some that block the production, which was interesting, and then the one that I was looking at, which was blocking the receptor, so VEGF can't bind. So common sense, looking at different ways to block the angiogenesis process. Again, by Folkman, a very key part of angiogenesis, and then talking about the different, types of therapies that are available. And then I think I remember talking about the limitations. See, I still remember my order of my thesis. I was talking about the limitations with them. So there were, I think, a lot of hypertension, bleeding, complications from the cardiac point of view, I'm trying to show, so here are some adverse reactions. I'm trying to show how my naturally derived compounds may be able to supplement the current anti-angiogenic therapy or regimen. So that's what that was about. This is another diagram showing the different ways of that mechanism for trying to stop angiogenesis. Then the key part was looking at drug resistance. So drug resistance, can happen for any drug, and anti-VEGF therapies do have their unfortunate issues. And this was really interesting diagram adapted from another paper showing the adaptive resistance and then the intrinsic, ones that are just not responding because they're trying to evade the inhibitors. So that, what was that about? And then just showing that, ways to counteract that resistance. So one of them was looking at alternative pathways, looking at other, antiangiogenic agents, which is what my thesis was about, or looking at modifying doses, or using other therapies to try and, target this issue. So this is, again, what I started to focus on in my thesis. So then I started to talk about, obviously, okay, how do you go about developing the drugs? What is the process? And then you got here, which is, the whole essentially cycle of making a drug, and then highlighting what I'll be focusing on, which is trying to generate a lead, trying to profile that lead, and trying to optimize it, which is what my PhD was actually about. So that's what that, and then looking at the different methods, the different ways, and then looking at, again, the general process, showing it in a different way, how from the biological point of view, so this was the chemistry point of view, so making the drug, profiling it, and then optimizing it. But from the biological point of view, is looking at how do you screen those compounds, how do you pick out one very quickly, and then what secondary assays do you do to try and pinpoint which one out of them is actually really important. So that's what that was for. And then some kind of, I remember some variables about what is important for making a preclinical candidate. I remember this now, the hit to lead optimization. So anybody in drug discovery, feel free to utilize my thesis if you would like. Then from there, I mentioned about how analog-based drug design is actually really, really important. And I remember the key example I gave was how this particular structure was interesting, but when they added a chlorine group to this particular aromatic ring, or they saw a very massive interaction by, I think, so their kinase inhibition, so their protein inhibition went up by 6-fold, only because they added a chlorine group at this position. So it increased their binding interactions, which set the scene for what I wanted to do my research for, which was trying to see if you modify the groups or modify the aromatic rings of these Chalcones structures, do you see an increase in activity, the preferred activity that we want to look at. So that's why I showed this example, right? To look, if you increase or add or modify or change the the functional groups around the edges, you might see an increase in what you want to see. So that was kind of my basis, my rationale for me modifying the Chalcones that I looked at. Then, now that I mentioned about how good analog-based drug design is, I started to talk about those scaffolds. So these are scaffolds is another word for the basic structure of your compound. So there's a lot to show about how many of them are being used to make drug discovery, and how many have been from a natural source. In particular, some of the drugs, 11 out of 12, 22 FDA drugs were used or modeled from natural products, kind of owing the natural element of my thesis. So that's what that was there for. And this is actually a basic structure of the Chalcones. So you see what I mean by, obviously you can't see me point, but if you see where the cursor is now, if I was to add functional groups here, could I see or change the activity that I wanted to see? Then a bit of a background about Chalcones, about where they're from, why were they looked at initially, why are they special, why not something else? And then some of the activities in literature of Chalcones reporting anti-angiogenic activity. So that's what that was there for. So that's what all of this is for. And then this is actually the basis of my entire thesis, which was why this particular one, so the one you see here, why was this so special? and other ones weren't. So my whole thesis was based on this particular piece of work. And then these are other examples of different chalcones. You can see over here, some will have methoxy groups, so these OME to OCH3. That's what that's there for, and other different variations as well. So that was the introduction to my thesis. So now aims and objectives. It's been quite a long video as well, so if you are still here, I appreciate it. So this was setting the scene now. So therefore the aims of was looking at, can we design, synthesize, or biologically evaluate a new series of these chalcone structures to see if they can be better than the parent compound. And the parent compound being that one I showed you earlier, which was 2-chloro and 2,5 orientation. I'll show you back on the screen so you know, which was this one. So that one is the one that we're interested in. So can we modify that more? Can we modify that a bit better? That's what that was looking at. So then I was looking at, right, can we understand from the parent compound which one is what is causing the activity in the first place? Then once we establish that, what can we do to try and improve it, trying to better it? So that's what this was there for. So that's the crux of the aims. Then obviously our hypothesis was essentially that if we do change it, we do change the proliferation, the migration of the parent compound, and obviously your null hypothesis is the opposite. So those were the aims of what we wanted to do, and then how we do it is your objectives. So this is the kind of how. So for those who are looking to make your aims and objectives, think of it as, you know, there's a discrepancy between the two. Aims is what you're looking to do, objectives is how you actually do it. So first is to design and make those derivatives of the parent compound, then screen them to see which one's interesting and try to understand, okay, what is integral to the activity observed. And then 3 is looking at some mimicking model to some degree of angiogenesis or anti-angiogenic activity, and then try and figure out to some degree the pathways involved or the proteins involved in that activity that was exerted. So now going into making the compounds, I looked at all sorts of, you know, chemistry, which I'll gloss over because I can't remember much of it. I remember I was linking chapters together, so something I bear in mind is here was about how to make the compounds, and then I mentioned chapter 4 will talk about actually the rationale or design of why I made these drugs. So this was just more about how to make it. So I had to really emphasize that in the thesis. So these were the different series. So one was changing this functional group over here and seeing how that changes the activity. One was looking at, okay, if you change this ring, is that important for the activity? So is it just this that was really important? And then series 3 was, if you make derivatives where you take bits off, at what point do you see the activity drop off? Series 4 was looking at this 2,4-diphenyl structure, and then series 5 was looking at the hydrogen donating versus hydrogen I think withdrawing. I can't remember exactly, but that was what series 5 was for. And then I looked at different, you know, approaches to making it. So you got this different catalysis, which I can't remember exactly, but I remember I used this benzaldehyde and acetophenone. For those who don't worry about it, I'm just mentioning chemistry things. And then this was one of the mechanisms. I completely forgot this. I wouldn't be able to write this out again, but at the time I was able to. So this was the base catalysis of my thesis. And then I was mentioning, okay, how it actually does it. So this was the written version of how it does all of that. And then looking at the acid catalysis. So this was looking at the acid version. So different version of catalysis and how it makes the actual compound. Again, won't be able to write it out, but you can see it now. And then description about, and this is where I was really leaning on Ken Beresford, who really helped me to understand this more and more. And then going down further, we have, so this is how I actually made the compounds. So here, for those who are interested, when you try to synthesize compound with OH group, they can interfere because OH is essentially, can be seen as a base. So you add a protective group. So this was tetrahydropyran here, and then so it protects the phenolic nature. Then you synthesize the compound together, and then you cleave it off. So that's how this is made. As you can see, this diagram explains it here. So you make it, and then you cleave it off, and then you're with your compound. Then I mentioned, oh yeah, I remember pyridinium p toluene sulfate. I remember when I was starting to understand these terms, I was like, this is nuts. This is like, and even though this is basic chemistry, this is not like super high end. This is fairly competent, even like master's level. So it wasn't super advanced because my PhD wasn't about the chemistry side. I wasn't trying to make a new version. I was trying to make new derivatives. And then talked about this particular procedure, how it went well, how I purified it, how I made these compounds using this procedure, and then looking at the analytical information about how the NMR values are because of this, and the FTIR is because of this, and talked about that more and more, and how you see this characteristic peaks for the compounds. So this is to do with the double bond in there. So you have I think I can't remember exactly, but it's to do with the trans configuration. I won't bore you with all of it, but this was proving to the examiners that the compound was mean was this orientation and not that orientation, essentially. And then this was showing, some HPLC work. This was the compound in methanol, so you can see it's very, very, very colourful, because chalcones are actually pigments for petals, actually. And then this was HPLC, so one peak showing, one compound at this particular wavelength, and then showing the yield, like if a if a melting point is quite short, it shows there's only one compound. So that's what that was there for. Not another type of in my thesis. So yeah, I think I couldn't find out the yield of this one, even though it wasn't a really important compound. But yeah, and then showing same thing again for all of these other compounds. And showing more about the chemistry information, which was that for, and then showing how I did it under pressurized conditions. So how I tried to make a compound, but in like a sealed vacuum to try and make it go quicker. So this is what we used. We didn't really yield many. I remember I struggled with that. Then some acid catalysis. So trying to make the compound very quick using acid instead of a base. And I think I yielded one compound, which really worked really well. And then acid catalysis for the other compounds, for some that I struggled with. And that's all this is there for. And then some methoxy groups, so compounds with OMe, so OCH3. I made them very simply, because they're very easy to make using this method. So these are all just to do with how I made the different compounds in my thesis. And again, some descriptions there. And then the conclusions about, why I felt this method worked and this one didn't, because of maybe the nature of the phenolic groups or the functional groups, and then going into detail with the chemistry about what happened and all of that stuff, and how I got lower yield or why this route was better and stuff like that. So that's what that was there for. And then now chapter 4 is looking at that high throughput screening, so how I screen the compounds for what I wanted to look at in terms of the compounds. So this is literally, as it says, screen compounds, try to figure out which one was interesting to take it further. So a little bit of an intro as to why screening is important, why I used this particular cell model as the model for me, and then why I used this particular colorimetric assay. So again, quite succinct, quite nice and forward. And then just showing how that actual assay works. Anybody who does cell culture might be familiar with the MTT assay. Very, very famous in the field. And then just showing how, we synthesize all of these as discussed in chapter 3 and trying to identify a hit compound. And then suggesting, why I use these particular concentrations and why they're relevant. And then just showing now different compounds. So this was the first group. So this was me talking about the activity, about how H9 showed protein activity, which is the compound in my thesis, and how the other ones maybe didn't, and how, you know, this is that. So essentially just contrasting, comparing the compounds and giving a bit of an insight as to why maybe they showed this compound and why they didn't here. And these were the compound and then the activity across 3 days, plus or minus the SEM, standard error of the mean. So you can see here some activities and then description about the data. And then again, same for all of them. So I'll just go through these. These are the same again. You can stop and you can obviously click on the link down in the video description if you want to have a read of this, but I don't want to bore you with it in the video so far. But this is giving insight of talking about what happened and then showing the data. So talking about what I saw, what was significant, why it wasn't, and then giving the data so far. And then went through all of that data, and then showing it all together. But look, this AH1 was the, you know, marker. AH9 was also good, and AH12 was good. And I'll talk about why I didn't take AH12 further. And this is the whole, you know, and word of advice, when you're writing any figure, make sure it's as if you don't need the rest of the thesis. That figure alone should be enough to understand what's actually happening. That was a very ingrained piece of advice a lot of my supervisors gave me, which was make sure you write everything in that figure caption, because it'll be useful for your paper, and you shouldn't need any part of your thesis to understand that figure. That figure caption should be enough. So word of advice, keep that in mind. So then we looked at the methoxy groups. So they actually showed an interesting promise, but I didn't have the time to take them further. So that's what that was there for. And then going further down, looking at the other groups. So these were the methoxy groups. And then how we compared it to sorafenib, which is a licensed inhibitor of the VEGFR receptor, and just looking at how it, you know, varies in terms of this particular model, even though that is more favorable as a drug itself because it's able to come into the body better, it doesn't break down and stuff like that. But we just wanted to compare and show that against the cell directly, AH1 and AH9 actually were quite favorable. Sorry. So that's that. And this was just an EC50 value. So EC50 is the concentration required to achieve 50% inhibition to your cell viability. So this was showing that. Sorafenib is a very potent, discontinued now inhibitor for angiogenesis. So we talked about that. But then we talked about the conclusion at the end of, you know, what this chapter showed about, you know, the viabilities, about the different series of drugs, and how, you know, this series showed this and that series showed that. But then a bit further down, again, how the methoxy groups, which was the 20 series, how they showed some interesting activity. And then here is when we showed that, okay, because AH12, as you saw earlier, was very interesting. It had a nitro group, which can be metabolized into an amine, which can lead to toxicity. So we elected that's not probably favorable as a drug candidate. So we took AH9 because of its better drug likeness, as you can see here. So that's why we took AH9 along with the parent compound AH1 forward. So we took it forward into our very basic functional assay. So this was looking at the migratory analysis of AH1 and AH9 against Vivex. So looking at, essentially, for those who may not be familiar with angiogenesis, there's endothelial cell migration. So if you can inhibit migration, you essentially can inhibit a part of angiogenesis. So the endothelial cells can't migrate to the tumor to establish a blood supply. So if you can stop that process, it'd be favorable to minimize cancer progression. So we talked about, you know, how there's different in vitro and in vivo assays, why we chose Huvex as still the choice, and then how there's different variations of the actual way to do this assay. So you can use different extracellular matrix, some people use it without, and how you can mimic what we see in the body. Again, just a reminder of the two compounds we're taking forward. Again, word of advice, you want to remind the examiner what they're looking at, so they don't have to go backwards. So which is why we put the compounds back here as well. And then, you know, going back to chapter 1, because you want to always relate back to literature, and always want to relate back to your previous chapters about, why are you looking at X, Y, and Z. So that's what that's for. And you can see, again, I link now chapter 4. So I'm reminding the examiners about, what's happened before and what we're going to be doing now. So that's what that was there for. Again, looking at why cell motility is a target for anti-cancer therapy, not just angiogenesis. So again, noting about the wound healing, why is it, a really useful assay, why is it simple, why is it helpful, and then looking at, evidences of people using anti-migratory, analysis to yield a candidate. And then talked about the assay. Again, I drew this on Adobe Draw, so Coco could have done a better job, but just a schematic about you should see the wound close over time, and if you don't, you're actually causing some anti-migratory activity. So again, talking about finding the right concentrations, the right time points, and then we had this picture here, which you can see here about at 10, you can start to see that the cells are starting to die off a bit, and 3 seem to be okay, and then 1 also seemed to be good. So I think we stopped 10 micromolar because I think we started to see some cell death. We want to make sure the cells were viable enough to differentiate or to migrate. I'm starting to realize that I'm showing my thesis and you might all be picking out mistakes and issues. If you are, let me know in the comment section down below. I'll be interested to see what you think. Then I was just showing the, essentially the width of the wound over time. So the percentage of the width of the wound, I'll show you it later down. And then these are some stats analysis about, H1, sorafenib, H9 at 0 hour, 4 hour, and 8 hours. You can see here, this is an example, and I use, kind of width of the wound. One of my own criticisms was I wish I used the area, because it's more representative, but this showed, that with nothing, you can see that the wound closed over time very easily. H1, did, impair wound closure, and sorafenib naturally. So this is proving that the assay works. So that's what that was there for. And these are some tabular results about, you can see that, look, untreated control, you can see the width of the wound clearly closes. This is the micrometers, whereas, at 3 micromolar for H1, you can see it didn't close as much there. And these are the percentage migrations of them over the 8 hours. You can see, you expect to see a lot of migration with the untreated control, and you should see a lower percentage with the others. But then this was the more colorful representation. You see the green is untreated control going down as we expected, but then the others actually inhibiting, and there were different ways to show this assay that we could normalize it, but we felt that at the time this was a better representation to show the discrepancies and how overall, despite the discrepancies, you can see that even with the lower concentration, we expect to see less inhibition, and as we did. So showing that, and again, as I mentioned, descriptions of the figure, and then we go now to the nice bit, which was AH9. So going into the stats here, and then as you can see naturally here, that at 3 micromolar, this was very significant. That it went from 500 micrometers to 100, but with 3 macromolars of H9, it barely went down at all. It only went down by 800, compared to sorafenib, which actually went down by nearly half. And you can see here, this was the key finding, that when you untreated control, you expect to see a lot of migration, but H9 blunted it. It stopped it for some reason, whereas sorafenib still inhibited it, but not as much as H9. So that was a key part, and you can see here that in red, because I chose in red because it's more visually appealing. Again, you've got to think about that when you're putting your figures together, that it didn't go down by much at all. So there was some anti-migratory activity occurring due to H9, and again, using a lower concentration, we showed that it dropped off, and with sorafenib in grey, again, we saw more migration in that, showing that in this particular model, H9 was superior in terms of causing anti-migratory activity. Then concluding the findings as to what was the difference between the migratory activity, because AH1 had a chlorine group, and AH9 had a bromine group. So was the bromine group, in terms of the chemistry, contributing to maybe binding to something within a receptor to cause the activity that we observed? That's what the thinking was at the time, and that was the main finding. So once we found that out, okay, how is it causing the migratory activity that we see? This was just a line representation of untreated control. So the width of the wound goes down, but you see H9, it's staying up. So with that in mind, what could we probe for that is key for the migration in terms of endothelial cells? So I could only do a bit more because this was the end of my thesis. I remember I had a lot of chemistry, so I could only do so much. So we set the scene about how the molecular mechanism of action is really important, and why that's really key to understanding how a drug works. That's what that's for. Then looking at the how we look at the different ways to do that. So we've got looking at proteins and why proteins are really important in terms of understanding drug receptors and drug kind of interactions, and then why I probe the case of looking at gel electrophoresis versus block. You have to justify, right? You have to justify why you did a certain technique. So we've got that over here, and then showing how nowadays, especially now in the past few years, you've got a lot more computational molecular docking type scenarios where you don't even need lab work. You can try and visually look at drug protein interactions. So that's what this was, looking at the pharmacological analysis of AH9 and trying to figure out what is it doing to certain proteins. So then, now that we set the scene about looking at proteins and looking at the MMOA, we looked at, right, as discussed in chapter 1, as we mentioned here, why VEGF is really important and how ERK, so MAPK ERK, how that's really important in the pathway for migration, and then linking it to chapter 5 about the migration. So then we looked at, okay, what does AH9 do to this in terms of phosphorylation, and then looking at the VEGFR2 receptor, which is the main receptor in angiogenesis, and then linking it to other papers that have looked at angiogenesis as well. So that's what that's there for, and then onto understanding why we look at these concentrations. Then looking at the actual, I don't know why. Oh yeah, I think it was an empty page. To looking at why we looked at 30 nanogram per mil of VEGF for 15 minutes prior to grabbing the cells for activation. So we've got that here, and then we've got the plots. You can see here that this is total ERK, this is phosphor ERK. When you don't add VEGF, there's no activation here, and then when you do add it, you see that you see a big band showing it activated. But then when you add AH9, you start to see it go less. I'll talk about why is it inverted in terms of concentration, and also when you add 30 micromolar of sorafenib, it completely silences the activity. So this was showing that things were working the way it's supposed to, and AH9 was actually doing something to a protein that's related to migration. So it's linking the story so far that we had before. And then a very interesting, but I remember in his story that I think I went out for dinner with my family at the time, and I printed this out because it was basically showing that's my PhD. That's this graph. I think I mentioned in an Instagram post as well. I spent 4 years to get to this point to produce this graph, which was showing that a compound that I made, that I synthesized, that I tested, was showing something interesting. And even though it's opposite way around, so you budding researchers might be looking at it and saying, why is the least concentrated the most active? Shouldn't it be like 100 micromolar should be the most active? And again, me being lazy, I didn't put the micromolar signs, I put the U sign. And the reason why was we thought that there was intracellular accumulation of the compound in vitro space, so it was essentially blocking its own activity because it was saturated, there was too much. But when we lowered the activity, in terms of the concentration, there was then enough space and enough time for the H9 to do its business. And what we also thought was there was a solubility issue at the higher concentrations where the compound started to precipitate a bit more in media, so maybe not much of it was actually getting in. So the two issues of not much of it actually going into the cell, and then number two, maybe too much of it was whatever actually got into the cell. we found that 10 micromolar was the right concentration, the right sweet spot to show the activity observed. Again, n equals 3, for those who are familiar with that. And sorafenib completely silenced ERK phosphorylation. Then we talked about VEGFR2, and this is something that was really annoying for me because I didn't have the time to get n equals 3 for this, which would have made my life a lot easier in terms of publishing my data by looking at the receptor level and then looking at the pathway level further down. So this was really frustrating that we couldn't get n equals 3 for this before I finished my PhD. But this was just showing very basically that there was some activity against the receptor in terms of just receptor expression, not looking at the active receptor, which is why sorafenib was still quite high. And then just linking it now back to literature, linking it now back to two different theses, two different papers, explaining why the 100 micromolar was not as potent as we expected, looking at why MAPK is important, and then summarizing the results, again very significant, that we saw here, linking it to chapters earlier, and trying to culminate and then finish the story nicely off. How we could look at other things in terms of other receptors, but how we can just mention this, which I'll make a bit smaller, how we think AH9 is affecting the receptor, but we know that AH9 is affecting this particular signaling molecule within the MAPK or the RAS-RAF MAPK pathway. I think I mentioned it somewhere. I think it's further down. I'll try to find it, but the RAS-RAF MEK pathway is what I'm talking about here. And then preliminary mechanism of action of H9. So this was the culmination of the end of that chapter. And then conclusions and findings. So just concluding everything now together as I'm trying to conclude this video. And then study limitations, not having issues with making the compounds, issues with waiting ages for things to arrive, issues with not having the cell line ready, issues with, maybe looking at the area of wound healing and not the kind of width, and then looking at maybe other assays to defend the anti-migratory activity. However, with the shortened window that I had to finish everything, it was enough justification to understand what's actually happening. And then simple future directions about maybe changing the compounds, or looking at synergistic interactions, looking at the mediators, natural things that you would understand when you get towards the end of your PhD about other avenues you want to go that you can't because you don't have enough time. And then concluding it off. And then experimental is essentially for those who are in the chemistry department, looking at the equipment that I used, how I actually made the compounds, and what methods I used to do the HPLC, the FTIR, the NMR. And then so this was the description as to how I made some of the compounds. And then so now you start to imagine if I was to show all of this stuff early on, it would be too chunky in the start of my thesis, so which is why we elected to pull it towards the end. So yeah, just to show you the rest of the thesis while we finish. This was the compound, and this is all the analytical information for anybody who wants to replicate making this compound. This is how you made it. This is what you should see in the melting points. This is what you should see in the TLC IR. This is how you can find the groups. This is the NMR information. This is the carbon NMR animation. This is the I think it's LCI. This is LCMS, and this is HPLC. It's all of these information needed to confirm what you made is the actual compound. And then more and more of this, all different compounds that I made, going on and on and on. So there's quite a lot that I made, thankfully, in my thesis. And then the biology side, the pharmacology side. So where I got the cells from, where I got the media from, the assay, what plates did I use, the Western blot stuff, what did I use, how did I do it, so what method did I use in terms of buffers, solutions, and then how I made those buffers. You can see over here. So if you guys are quite new, feel free to borrow, steal this, however way you want to look at it, in terms of making your own buffers. You can find this online as well, but if you're already reading it, feel free. A little bit of how to make your own ECL, so a little bit of a sneak peek. So for those who have gone this far into this video, I appreciate it. And if you are doing any protein work, this is how you can make your own ECL to save a lot of money. So this is my little gift to you because you stayed so long in this video. You'll be interested to know you save a lot of money. So all the buns you saw earlier was using homemade ECL. So we saved hundreds and hundreds of pounds. These are the antibodies that I used. And then obviously the method of how I did the cell culture, how I made stock solutions or compounds, the actual description of how I did the cell viability assay, the MTT assay, how I got the cells stimulated in terms of, you know, preparations for the protein work, which was the chapter 6, and then this classical how you did random gels, how you transferred it, how you stained them, how you detected them, how I did the scratch assay, and obviously just a little disclaimer about statistical analysis, and then plenty of references. So a lot longer than I thought, but that was a little bit of a crash course into how I did my thesis. I walked through my PhD and my thesis and how I did certain things, a little bit of nuances towards that. Hopefully it will help you in terms of why I did it in this way and that way, and feel free to, like I said, utilize it as a template or things to learn from. But hopefully, I know that was a longer video, but hopefully you enjoyed that walkthrough. If you did enjoy some of them, do let me know in the comment section down below which chapter you enjoyed the most or which tip you enjoyed the most. And if you want more kind of reaction videos like this about me reading a paper or me reading somebody else's thesis or video, let me know down below as well. Do consider subscribing if you can. As you can see, I'm now running out of energy because I'm tired. But I really appreciate you in watching it for this long. And I do sincerely hope you found it beneficial. But in any case, I shall see you in the next one. Thank you so much for watching, and I will hopefully see you soon. Take care.